Hello, I welcome you all in this course on mechanical measurement systems. Today we will discuss air pollution sampling and measurement. Topics to be covered today are units for pollution measurement first of all, followed by general air sampling train, gas sampling techniques, particulate sampling techniques, opacity measurements and Orsat apparatus. The pollution is everybody's concern nowadays, and for the purpose of pollution abatement, pollution metering is important. Until unless we measure the pollution, we cannot quantify the pollution. If we are not able to quantify the pollution, we cannot reduce the pollution. So, pollution is expressed in terms of volumetric units, that is parts per million, right? And parts per million can be defined as volume of the gaseous pollutant, whatever the volume is there, right, divided by 10 to power 6 volume of the gas plus volume of the air. So, it is volume to volume ratio. Parts per million is volume to volume ratio. Another way of expressing the pollutants is grams per meter cube. That is expression in the basis of unit which is based on the mass, grams per meter cube, or it can be expressed in terms of ppm. ppb is also there in some of the pollutants like ozone. Ozone is expressed in terms of ppb, parts per billion. But these type of expressions are quite rare. Normally they are expressed in terms of parts per million. And parts per million, this volume can always be converted into the mass based type of system using the ideal gas equation PV is equal to RT, provided we know the value of R for the pollutant, right, polluting gas. So, this equation can convert the volume base to the mass base and vice versa. Mass base also can be converted into the volume base expression. Now, local, state and nation agencies, they set pollution standards, certain standards for the pollution, and they have to be adhered. And for enforcement of the standards of the pollution, there are two ways of doing it. I mean, first is monitoring the pollution in the air or monitoring the pollution at the source. So, monitoring the pollution in ambient air gives us the gross effect of all the sources. That is also important. I mean, gross effect of all the sources. So, ambient air pollution gives the gross effect. This has to be monitored first of all. And second thing is pollution at source. For control purpose, we have to monitor or we have to meter the pollution at the source, because we cannot control the gross effect. I mean, if ambient air is polluted, it cannot be controlled. For controlling the pollution in the ambient air, the pollution has to be controlled at the source. For example, chimney in a factory. So it has to be ensured. It has to be ensured by the agencies that the whatever emission is coming out of the chimneys is sticking to the pollution norms, or whatever water is being drained off of the industry, it is adhering to the pollution norms, right? So the measurement of pollution or pollutants is nowadays a very important activity, because it directly affects the human health. Pollution in the air directly affects the human health. But imposition of strict pollution standards may cause severe economic dislocations on local, state and nation level. I mean, Taj Mahal is a very good example for that. When the concern was raised for the damage of Taj due to the pollutants in the air, many of the industries in Agra were closed, especially industries which were coal-based industries, and specifically the casting in the coal-based casting. Either they had to shift to the new technology or they have to close down. They had no other option. So it is a, I mean, severe economic dislocation on local, state and nation level. This may result in unemployment also. If you are adhering to the strict pollution norms, it may lead to the unemployment also. Because many of the industries may not be able to install the latest technology. I mean, financially it may not be viable for them. So they will close down. This may cause unemployment. And but these are political economic factors, but the fact is, at any case, we have to control the pollution. If we don't control the pollution, it is because nowadays it is becoming a threat for the human race. So at any cost, a country has to control the pollution, and for controlling the pollution, it has to be measured first, right? So there are certain techniques for pollution measurement. So first of all, air sampling has to be done. Air sampling. Now, for the purpose of air sampling, we need sample collection equipment. First of all, equipment. Right? Because we cannot simply pick the air from the atmosphere and or from effluent and just measure it. So there has to be some sampling collection devices which can collect the air sample. Then some conditioning devices are used which can condition the sample, because there may be some undesired particles or the gases in the sample which are not required, right? So they have to be filtered out. So sample conditioning devices, sample collection equipment, metering devices are important. And then there is a vacuum source. So vacuum source is required to pull the air. So it is called air pollution air sampling train. Right. So in air sampling train, there is one inlet for air sample. Now this air sample will go to the sample conditioning unit. Sample conditioning, right? Now after sampling conditioning, it will go to the sample collection unit, and sample collection unit is normally having two parts. First of all, collection, and second is analysis. Analysis is also done here, and this is a part of sample collection, right? And after sample collection, it goes to another unit where flow and temperature measurement is done, right? Now after metering the flow and temperature, post sample conditioning is done. Post sample conditioning, right? And lastly, there is a vacuum source. So this is air sampling train. So the air sample is entering from this side and leaving from this side, and this is how the analysis can be arranged. Analysis for the air sampling can be arranged, and the first activity here is the filtration, because whenever we take air into for the sampling purpose, first it has to be filtered. Foreign particles have to be removed. So filtration is the first activity. So air sampling which is coming in, it has to be filtered. So in the filtration, it is also, the sample is also dried to remove the vapors of water, right? So the water vapors are removed, or we can saturate it entirely with the water vapor for the later reference, that the air was completely saturated for the later reference in the case of analysis. Unwanted pollutants are also removed in filtration, maybe through some reaction. So unwanted pollutants are also, so there is a cleaning of the sample. The filtration is a sort of cleaning of the sample of air. Now for gas collection, now the gas which has entered, it has to be collected. Now collection, there can be two ways of gas collection. One is absorption, and another is adsorption. Now, in process of absorption, the gas is absorbed by the liquid, or it is simply dissolved in the liquid. It is absorption of the gas takes place in the liquid. In adsorption, there is the gas remains on the surface. It is adsorptions are solids, and the gas remains at the surface. It remains on the surface. It forms a layer on the surface. It does not penetrate the adsorption, but this adsorption process is very effective. Something like if you put a chalk in ink, when you break the chalk, you will find that ink is, the color of the ink is remaining at the periphery of the chalk only. It does not penetrate into the chalk. So, adsorption activity, something like this. However, in the case of absorption, the absorption may be through chemical reaction also, right. Now, the third one is the condensation of the vapor. Suppose the gas is coming, some of the pollutants can be removed, or the pollutants have already been removed. So, gas can be absorbed by condensation and freezing out. It is put to the lower chamber. There can be number of chambers at different temperatures. So, the gases or in the mixture are condensed at different pressures, different temperatures, and they are collected at one place, right. So, this is about the gas collection. After the gas collection, we have to remove the particulates from the gas. So, filtration is done in singles. Filtration is also done in single stage and multi stages. This is also done in single stage, or it can take place in number of stages. For example, there is a wet cloth, right, and if you pass air through the wet cloth, number of the particle will be sticking to the wet cloth. That is how the cleaning can take place. Wet or dry impingers can be used for removing the particulates, right. Sediments will settle and they will also be removed. So, ultimately when the sample is ready, after filtration and preparation of the sample or absorption of the gas, then analysis of the gas analysis can be done. In absorption techniques, impingers, atomizing scrubbers, fritted glass scrubbers, or some type of packed column can be used for absorption type of system. In adsorption system, it is activated carbon is nowadays is very much used for the absorption process. Activated alumina, silica gel and molecular sieves can be used for the adsorption technique of gas sampling. So, when sample is there, I mean either through absorption, through adsorption, or by condensation and freeze out techniques. Now, sample is ready, right. Now, this sample has to be analyzed and the level of pollution in the air has to be determined. Now, there is a particulate sampling technique. Now, the range of particulate matter encountered in air is ranges between 0.001 to 500 micrometer. The range is quite large. Now, settling and sedimentation, and there is the two techniques, settling and sedimentation and mechanical collection. Separation of the particles, first is settling. Settling and sedimentation. If I said earlier, if the particle size is large, it will settle and it will and it can be collected at one time if the sufficient length of time is given for the settlement. So, the sample is taken and it is left for a long time. Let us say 24 hours or 48 hours. So, particles, they will slightly, whatever the size is, if the size is 0.1 micron, it may not come down. Less than 0.1, it may not come down, but particles, other particles will slowly settle at the bottom of the vessel. But we have to give a time period of maybe 24 hours, 28 hours, 48 hours or 72 hours, depending, it depends upon the size of the particles also. If the size is large, settlement will be faster, right? But it is difficult to, I mean, once you take the sample and leave the pot for 1 or 2 or 3 days and then see how much sedimentation has been done, and still all the particles will not settle down during that duration, that is also possible. So it is a very time consuming and tedious process. Another is mechanical collection. In mechanical collection, there is a grab volume, and it's a simply a tube and having walls on both the sides, right? And this grab tube, this side is connected to the vacuum, some vacuum pump, right? And this, whatever the air is coming from this side, it is collected in the tube. But the issue remains that concentration is disturbed or it is not disturbed when we are taking the sample, because already air is there inside this tube, right? So concentration has disturbed or it has not disturbed. If it is disturbed, so what we can do, we can flush the sample, filtration techniques. Now, in some other filtration techniques, a glass fiber paper can be taken, paper can be taken, and this glass fiber type of paper, the sample is passed through this paper for 24 hours, right? And the flow rate is about 1.5 meter cube per minute, right? And for ordinary filter paper can also be taken for the particle size in the range of 0.5 to 1.0 micrometers. Now, if we want to have, I mean, the particles are of the size of the 0.5 to 1 micrometer, ordinary filter paper can also work. And for small volume samples, porous ceramic, fritted glass, they can, I mean, we can use different type of filters for the purpose of filtration. Suppose filtration is less than, suppose the particle size is less than 0.1 micrometer, right? So in that case, membranes or molecular filters can also be used, but normally we don't require measurement of the particles less than 0.1 micrometers, right? Now, result of such measurement is expressed. Now, this filtration result is expressed in terms of coefficient of Haze, COH. COH, coefficient of Haze. Now, coefficient of Haze is expressed in terms of optical density OD divided by 0.1. Now, what is optical density? Optical density is log I over IO. Intensity when before the use and intensity after the use. I over IO, that is intensity of the light before use and this is after the use, right? And opacity, this is known as I by IO, is also known as opacity of the paper. So it is simply just passing the sample over the paper, the transparency of the paper will reduce, or right, and paper will tend to become more and more opaque if the pollution level is high, and this is quantified by coefficient of Haze. Now, after the coefficient of Haze, we can discuss one very important device which is used for especially flue gas analysis. And for the purpose of flue gas analysis, Orsat type of apparatus is used. Orsat apparatus is used. So, for the purpose of analysis of flue gases, Orsat apparatus is used, right? So, Orsat apparatus. In Orsat apparatus, because in the flue gases, the main pollutant in the flue gases are this carbon dioxide, carbon monoxide, and we have to find the level of oxygen also in order to find the excess air, right? So, in Orsat apparatus, there are 3 tubes filled with the different reagents. So, they are flasks actually, they are not tubes, they are flasks. They are filled with different reagents. And in fact, they are bent backward. If you look at the side view is going to be like this. And they are filled with the glass tubes also, glass rods also, just to increase. They are filled with the, number of glass tubes just to increase the surface area of the contact, right? So, it is filled up to here, and this is the front which we are seeing. On the back side, there is an oil so that the reagent does not evaporate from the back side. So, it is from elevation, it appears to be a single flask, but it is a combination of 2 flasks, right? And on the backside flask, it is filled with the oil so that there is no evaporation of these reagents. Let us label them flask 1, flask 2, and flask 3. Now, flask 1 consists of KOH, potassium hydroxide, and it is in 1:2 ratio of water mass to mass or weight to weight. Weight to weight ratio with water. It is a 10 grams of KOH, it is mixed with the 20 grams of water. So, this mixture is present in flask 1, and this is used for absorption of CO2. So, this is for absorption of CO2. Now, another one is pyrogolic acid. This is flask 2, pyrogolic acid, and pyrogolic acid is 5 grams in 15 cc of water. 5 grams of pyrogolic acid in 15 cc of water with 120 grams of KOH in 80 cc of water. So, it's a mixture. So, it is present here for the absorption of oxygen, right? And in the third one is cuprous chloride, right? Cuprous chloride is dissolved in 1:20 weight to weight ratio of HCl till it becomes colorless. So, these are 3 chemicals filled in these flasks, and they are connected by a common header. A common header is there, and all are connected to common header. Right? After connection to the common header, and there is a valve here. So, anytime it can be opened and it can be closed. This is the common header. Now, sample has to come from this side, right? And before sample, there is a cotton wool filter to remove the foreign particles, filter, right? Now, before filter, there is a aspirator bulb here, which sucks the sample, and it comes from a U tube, which is filled with the calcium chloride. in order to remove any moisture in the, so it is a dry sample, dry sampling entering the header, and from header it can be sent to different jars. Okay. Now on this side, there is a eudiometer, and which has marked on it, or in the scale is fixed next to the eudiometer, and then there is a aspirator bottle filled with water. There is a aspirator bottle. There is a three-way valve is also somewhere here. Three-way valve. Three-way valve is also there. Right? Now, there is a flexible hose. Okay, flexible hose is here. This is filled water. And these have, all jars have a mark at the top. So initially what we are going to do, we are just going to lift this jar. So all the air will is replaced. First of all, setup is clean, all the valves are checked, and then this bottle is lifted, and this is also put under a cooling water jacket, because flue gases may be hot. So this is put under cooling water jacket, so temperature remains constant here. So for initially the glass is lifted, this bottle is lifted, and all the air inside the system is removed. These valves are closed, right? And then flue gases are sucked in, right? And this process is carried out by just opening valve this 2-3 times, so that all the air inside the system is removed. Then finally a sample is taken in. First, this valve is open, right? And this jar is opened 2-3 times, is moved 2-3 times, so that there is a proper movement of, or proper absorption of carbon dioxide here, right? And then jar is lowered or up or moved up. When this liquid touches this mark, the valve is closed. So initially, so first of all, initial volume is noted here. Initial volume, normally it is, ideally it is 100 cc, but it can be 95, 90 cc also, or 105 cc also. But ideally it should be 100 cc. So constant valve is sucked in. After absorption, here again the volume is noted. Naturally the volume is reduced. It may reduce to, let us say, 100 cc to 90 cc. Then again this valve is opened. This movable jar bottle is lifted. The entire volume from here enters here. The oxygen gets absorbed here. Then again the bottle is lowered, and when this fluid touches this mark, this valve is closed. Same is the process repeated here, and every time you will find that there is a reduction in volume. And this reduction in volume is noted, and this reduction in volume ultimately leads to the finding out the concentration of CO2, O2 and CO in the flue gases. And this is a volumetric analysis. We get the volumes, and through this we can also find the excess air in the flue gases. Because when the fuel is burned, it is rare that the entire fuel is burned with a stoichiometric ratio, stoichiometric air. What happens, even if we supply excess of air, 10% or 20%, some of the fuel remains unburned, and that is why the CO is formed, right? And we can take one example for better understanding of the working of Orsat apparatus. In Orsat apparatus, the readings I'll write on the blackboard. Readings I'll write on the board. Now, suppose initial volume is 95 cc. After CO2 absorption, the volume is reduced to 83 cc. After oxygen absorption, the volume is reduced to 79 cc. And after CO absorption, the volume is reduced to 78 cc. So in an Orsat apparatus, initial sample volume is 95 cc, and these are the volumes after absorption. So the volume of CO2 is 95 minus 83 is equal to 12 cc. Volume of oxygen is equal to 83 minus 79 is equal to 4 cc. And volume of CO is equal to 79 minus 78 is equal to 1 cc. Right? And after this, after doing this, we will try to find the volume friction of this. So volume friction will lead to the mole friction also. So mole of CO2 is equal to 12 by 95 into 100 is equal to 12.6%. For oxygen, it is going to be 4 by 95 into 100. It is going to be 4.2%. And for CO, it is going to be 1 by 95 into 100 is equal to 1.05%. Now, I want to find the excess air which is supplied. So for excess air, we will have to write the equation, the combustion equation, right? And it is the fuel which is burned is methane. So fuel which is burned in methane means, suppose A moles of methane are reacting with X of oxygen and plus 3.76 of X of nitrogen. When X is oxygen, then 3.76 is nitrogen, and it is making, now let us say 12 of CO2, 4 of O2 plus 1 of CO plus some water, and water is also, let us have some constant for water also. So water is BH2O plus 3.76x nitrogen. Nitrogen will not participate in the reaction. Now if we make the balance, then A carbon, A is equal to 12 plus 1 is equal to 13, right? And for hydrogen balance, 4A is equal to 2B. So B is equal to 26. This is from hydrogen balance. And then oxygen. So 2x is equal to 12 into 2 plus 4 into 2 plus 1 plus oxygen 12 into 2, 4 into 2 plus 1 plus B. B is equal to 26. Right? And this is going to be equal to 59. So X is equal to 29.5. Okay. Now we can put the value of A, B and X and we can balance this equation. Now this equation, the air fuel ratio, air fuel ratio is going to be mass of the air divided by mass of ammonia. Sorry, this methane. Mass of air is 29.5 oxygen plus 3.76 nitrogen. We are considering air is a mixture of oxygen and nitrogen. And mass of ammonia, the value of A was 13. So 13, 12 plus 4. Mass of this methane. So mass of the methane, CH4, the C for 12 for C and 4 for H4. Right? And this will give the air fuel ratio as 19.47. It means 19.47 kg of air is supplied to burn 1 kg of methane. But actually how much air is required? So actually if we are required, so we will have to write the combustion equation again for the burning of methane, that is 13CH4 plus 26O2 plus 3.76 into 26 N2 is equal to 13 CO2 plus 26 H2O plus 3.76 to 26 N2. This is the minimum oxygen requirement. This is the minimum oxygen requirement for burning of the methane. And for this, an actual oxygen supplied was 29.5, if you remember. So if you want to have excess of air, and that is going to be percentage excess of air is going to be 29.5 minus 26 divided by 26 into 100, and that is 13.5%. So with the help of this Orsat apparatus analysis for the flue gases, we can also find how much excess air is supplied for the burning of the fuel. That is all for today. Thank you very much.